So my talk is on integrating cybersecurity and data science, artificial intelligence with applications in Internet of Transportation and infrastructures. And so the outline, so there are three parts. The first part is on integrating cybersecurity, AI, and data science. And in particular, I'll talk about big data security and privacy, how we got motivated to do this work. And then very briefly on privacy-aware quantified self, some of the work that we are doing on developing a policy-based privacy-aware data management system. And then I will talk about data science for cybersecurity applications. And something that is unique here is stream data analytics or stream mining. And then, of course, what happens if the machine learning techniques are attacked? And so here I'm talking about securing data science ML. It's a very hot topic these days, but we started this work around 10 years ago and published a paper in KDD in 2012. And since then, we've had a few papers on this topic. And then talking about trustworthy machine learning, and in particular, how do we integrate cybersecurity and machine learning with formal methods? So that's an area I believe that needs a lot of work. So part 2 is security and privacy for Internet of Transportation and infrastructures. And then part 3 is actually what we are currently working on, applying part 1 to part 2. And so that's what I'm discussing. So this work has been sponsored by a number of organizations, NSF, ARO, Air Force, NASA, NIST, NSA, and a number of colleagues, Professor Alvaro Cardenas, Professor Murat Kantajalu, Professor Latifa Khan, and our former PhD student, myself and Professor Cardenas, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1, integrating cybersecurity and AI, ML, data science. So I'm trying to cover a lot of topics within this short space of time to sort of motivate and generate, more research in this area. Okay, so, right. So the motivation is, of course, we go back to about 20 years now, data mining, security, and privacy. So I believe that I introduced this idea, data mining for security and then privacy. That was in 1996 at the IFIP 11.3 Data and Application Security Conference. And later, there was a keynote address. Later, I gave a keynote at the Pacific Asia Data Mining Conference, and that was in 1998 in Melbourne. So first one was in Como, Italy, and the second was in Melbourne, Australia. And then I sort of call it a landmark paper only because I was a program director at NSF in 2000, from 2001 to 2004. So there were a lot of discussions soon after 9/11 about data mining, security, and privacy, right? Congress was involved. And that was all because Admiral Poindexter, he was the head of DARPA's terrorism awareness program. And then he talked about collecting data of every American. So people got very concerned. And then after that, there was a moratorium on the word data mining. Of course, now we have data science. Anyway, so I published a paper on data mining, national security, privacy, and civil liberties. And it's interesting because almost 20 years later, last year, I published another paper, but I was not at NSF at this time last year. So I wouldn't call it a landmark paper. So I will call it why it was landmark. So, on data science, instead of national security, I said COVID-19 and privacy and civil liberties. There were a lot of differences, some differences, I would say, between 2001 and 2020. Anyway, because when you are a program director and when you publish a paper, of course, many people reference that paper, and that sort of spawned a new area of research, and I funded a lot of efforts. Although this whole area of privacy preserving data mining was first developed at IBM, Rakesh Agarwal and some of his colleagues. And so what they did was you have, original data, and then you add noise, then you get the noise added data, and then you have a modified data mining process. But the final result should be the same. Otherwise, what's the point in doing data mining? Because you want to get useful results. So at that time, as I said, I was at NSF, IPA from the MITRE Corporation in Massachusetts. And then in fall 2004, I joined UT Dallas. And together with our colleague, Professor Murat Kantajulu, we had our first joint PhD student. And she focused on privacy preserving decision trees and came up with a very novel method, perturbation method. And so several years later, this was in 2014, I organized a workshop because data mining, security, and privacy, it's now exacerbated due to big data, data science, machine learning, because you can do much more powerful things and put things together and infer stuff that was previously unknown. Or highly private data, right, from the various publicly available pieces of data. So I hosted an NSF workshop and then presented the results to an interagency working group in February 2015 in Washington. And then after that, there were several efforts on privacy. There was also the Brandeis program at DARPA. So anyway, there's a lot of interest on privacy, especially not just with data science, but also because of COVID-19. Okay, so what was a summary of the workshop? So we said, okay, it's very, it's known, right? Technological advances, novel applications, because we can capture, analyze large amounts of data, even for security tasks, like for authentication, access control. So for two-factor authentication, you need to write your fingerprint or your facial recognition and so on. As a result, privacy could be violated. And so you analyze the integrated data on the web, and that can help identify connections, relationships, disease outbreaks, and so on, right? So even if you anonymize the data by removing the identifiers, when you put all these records together and link them, you could re-identify the individuals. And so security tasks such as authentication, access control, they require, as I said, multi-factor authentication. Information could be stolen. And so the directions we discussed at the workshop, various access control models. So Professor Elisa Bertino was lead in that area. And Murat was lead Kantajulu on privacy enhanced techniques. And I think there was someone else focused on big data for cybersecurity. At that time, we didn't really focus on machine learning, secure machine learning. Although we had done some work and published our first KDD paper in 2012, there wasn't as much focus here, but this is the area there's a lot of interest these days. Okay, so as a result of the workshop, we started a project on privacy-aware quantified self. So what is quantified self, right? You've got all these mobile devices that, you collect lots of data. There are billions of users, right? So lots of data is being collected about us, and we know that, that's no secret. But there is this quantified self movement that psychologists and sociologists have been working, right? Because what they are saying is collect lots of data about people and then give advice to people about health habits. Like, for example, I love vanilla ice cream and milk chocolates. Fortunately, I don't keep any in the refrigerator, but suppose I do. Then when I open the refrigerator, I know that I will go for vanilla ice cream and milk chocolates. Wouldn't it be great if the refrigerator would tell me, look, or my smartphone will tell me, don't touch the vanilla ice cream or milk chocolates, right? So psychologists and sociologists, healthcare experts and so on felt that would be really useful. Collecting lots of data. Data could be shared with other service providers, cloud-based services, and so on. But once you start collecting the data and sharing, of course, the privacy could be violated. For example, data collected by a device to monitor glucose levels might be used by insurance companies, not just to deny coverage for me, but also my son and my grandson, right? So that's very dangerous because all your descendants, if you have diabetes, then all your descendants could be also denied coverage. So such privacy violations could easily get out of control if data collectors could aggregate financial and health data, tweets, Facebook activity, and so on. So to address these challenges, we need sort of privacy-aware quantified self. So as you can see, right, lots of data being collected, Fitbits and so on. Okay. So what we are developing, right, it's much of the project is sort of completed. You have health related information, fitness data, location, social media, and so on. Lots of data being collected on a smartphone, data collection, storage, analytics, some encrypted in the cloud and some anonymized, and there is cloud-based services. So this is what we are developing almost, which is complete. Privacy aware quantified self-manager. So what we are saying is that policies guide every step of the way, right? Data collection policies, data storage policies, data analytics policies, data sharing policies. And one of the interesting things that we are just beginning to look at is so how do you ensure the security, in the sense that, of course, you have to enforce these policies, right? The privacy policies. But how do you know that you enforce these privacy policies correctly? Although we didn't incorporate that piece into this work, we can use blockchain or distributed ledger technology to enforce that security, to ensure that all of the work, because these are really contracts when you talk about policies. So there are, we are just starting that work, but I also noticed that there are quite a few others who have also published papers on blockchain and data sharing. Okay, so that's one piece of work, privacy. Now, so policy aware data collection, storage, access, analytics sharing. So as we said, I pretty much said everything. So this is what we are developing or almost developed. Cloud-based services, so lots of data being collected. Some of the data could be pushed into the cloud. Based on access control policies, local apps running on the device will be given access to some of the data. And when needed, these apps will be allowed to access some of the encrypted data, right? Built a simple query interface. So sometimes data may not be needed, say fine grain. You don't have to weigh a perfectly healthy 20-year-old. You don't have to weigh him or her every day, right? But a 70-year-old, even if he or she or even 80 perfectly healthy, you never know. There could be some aspects, some problems. So that's why you don't want to sort of collect too much data. In other cases, data may have to be deleted. And again, what are the deletion policies? Is the data really deleted? Right? We envision data sharing and analytics will be carried out using services. And based on different scenarios, data will be sent without modification, sometimes sanitization, and so on. Okay, so that's the privacy part. Now, so we talked about big data security and privacy. So how we got motivated about privacy, preserving data mining, then big data security and privacy, what we are doing on policy-based data collection and sharing, and then data science for cybersecurity applications. This is joint work with my colleague, Latifa Khan, and also Professor Jay Han from Urbana-Champaign. So again, the challenge here, and something unique that we developed, is that you have data is coming in streams. Okay, so typically with data mining, machine learning, you use past data to build classification models, predict the labels of future instances, and that helps decision making. So you can ask the question, so what's new? This has been done for 20 years. Or even longer, right? The challenge is lots and lots of data are arriving, like network traffic, stock market data. So it's a continuous flow of data, very common in a connected world, massive amounts of data. So for instance, the challenge here, the concepts are changing. Today you say buy Microsoft, tomorrow it's buy Google, the next day you buy Facebook, the other day buy the stocks of Amazon. So the concepts are changing. One classification model does not satisfy all the concepts, right? So when I was at NSF 2001 to 2004, research was just beginning on something called real-time data mining, but there wasn't really, not much progress was made. But then by around 2000, so we started working in this particular aspect sponsored by NASA around 2008, and we've done a lot of work, applied it to a number of applications. So what did we do? So we developed an ensemble-based classification models, and the bad models or outdated models are thrown, because typically for machine learning, you have got this one model that you apply. So we have an ensemble models. These models are talking to each other and then throwing away models that are outdated. and keeping up the current models. And so you train an ensemble of models, and then of course you test, and then if it's benign, you store it in some server for further analysis, and attack you quarantine. Right? You could have an expert human in the loop, but these models are talking classification models. They are communicating with each other and deciding which ones to throw away. And so we applied it for a number of applications, website fingerprinting, and so on. So one such application, the DoD was very interested at the time. This was around 6-7 years ago, on insider threat detection. So I really, for the lack of time, I don't want to take too much time. So insider threat requires, the bad people pretending to be good people, right? It could be, sort of the enemy adversary, the spies, right, pretending to be good. And so that's one thing. Or it could also be malicious processes, pretending to be, good processes. And so we have applied our an ensemble-based stream mining algorithms or stream analytics, both supervised and unsupervised. In particular, we use a lot support vector machine, one class traditional and one class. And then we have also designed and developed unsupervised ensemble-based learning algorithms, maintaining a compressed dictionary, like repetitive sequences found throughout dynamic data streams, unbounded length. In unsupervised learning, compression techniques are used to model like common behavior. So we got results in classify exhibiting a substantial increasing in classification accuracy. So ensemble of classifiers allows the unsupervised approach to outperform traditional static learning approaches and boost effectiveness. So it was a bit unusual that we got this sort of interesting result. Of course, typically of machine learning, it's very hard to find out why it's performing. That's why all this explainable AI, explainable machine learning, that's going to help us a lot. Why certain things are happening certain way. Okay, so application architecture for the same thing, insider threat detection. So we have system calls, we have I chunks that we train, and then I+1 chunk is when we test. So of course, extracting features, gathering all the data. And what is unique here, or at least at the time, was this ensemble of models and applying these learning algorithms, and one class support vector machine and support vector machine for supervised and graph-based anomaly detection. And of course, that's the training part. And of course, testing, we extract features and then apply these models. Of course, these models are talking to each other. And when it's outdated, because remember, data is arriving in streams. And so here, all kinds of system calls that the user is typing. And so when data gets outdated, or models get outdated, you throw it away, right? And so then you test, and we had some fairly accurate results. Okay, so that is data science, machine learning for cybersecurity. Now we come to adversarial machine learning. This is sort of one of the biggest problems, but I have to, it's sort of interesting. I've thought a lot. I worked in this field, in this particular area for about 12 years. And it's a little bit sort of frustrating. I'll tell you why. Okay, so adversary modifies data to defeat. So we are learning, right, our models. Adversaries try to thwart our models, right? So this could be really huge in the sense that, this could be drug companies, especially the race for COVID-19 vaccines, right? The adversary could be another pharmaceutical company, could attack and not only try to steal our secrets, try to thwart our models so that bad results are produced, right? If you have bad data, it's like garbage in, garbage out. So understand adversarial learning. It's not concept drift, like I discussed earlier. It's not online learning. Adversary adapts to avoid being detected during training time, data poisoning during test time, modifying features when data mining is deployed. So there is sort of a game that is being played between data miner or data science or machine learning model and the adversary. So you can see this is the traditional support vector machine. You have these blue circles, which are good instances, and the red squares are bad instances. So see what happens, right? What the adversary is trying to do is to learn the models and the data and push the red squares below this line, the boundary line, so that they won't be caught. So these 1, 2, 3, 4, 5 instances will not be caught, right? So So that's going to give us what? False negatives. And that's not good. We don't want false positives. We don't want false negatives. And so before I go further, we looked at two different types of models. One is the free range attack. The other one is the targeted attack. Free range attack is essentially adversary can move the malicious data anywhere in the domain, right? Anywhere there's a lower bound and upper bound. CF is between 0 and 1. And so this is sort of the free range attack. I won't go more into the details. Our KDD paper and some of the other papers discuss more, but I'll tell you the problem. So, okay, before I go into the problem, right, so this is the support vector machine, a traditional line, the dashed line. The blue line is by applying this model and game theoretic techniques, we are pushing the boundary to this place here. So you can see there is, by pushing it, right, some of the, so that's, okay, so you have the red squares are bad and the green circles are good. But what happens where here, some of the red crosses are not caught, right? But by moving the line, it's caught. And that's what same thing I'm saying here, right? So black dashed line is a standard classification boundary support vector machine. Blue line is the adversarial support vector machine. Threat model, test time deployment attacks, attacker models, X to X prime. It can, different types of attacks, right? Modify packet length by adding dummy bytes, add good word to spam email, add noise to image. So you can see, right, by moving the blue line, right, some of the bad instances are really being caught. It would not have been caught. But the problem is, you can ask the question, why don't we move this line right here? Then all the bad instances will be caught. But if we move it here, some of the good instances are also showing up as bad instances. So as I said, we don't want false positives and we don't want false negatives. Okay, so before I go to the next part, one of the problems I find, look, we are only talking about a limited number of attacks, free range and sort of targeted attacks. In the real world, we could have hundreds of attacks, right? So how can we handle all of those attacks, or at least even a good number of those attacks, and build adversarial support vector machine or adversarial machine learning models, right? It's going to be really very difficult. While it could be a very interesting sort of mathematical exercise, because game theory is really very exciting, very challenging intellectually, but then is it really going to work, right? So that's something that I've been a little bit concerned about. And that's when, you know, I really think that trustworthy analytics, and there's others also are talking about it, like Professor Somesh Jha is, you know, from University of Wisconsin Madison. He's really quite an expert in this area. So that's, and recently I was participating in the Army's strategic planning. That was in March of this year. And so I really wrote up something together with Professor Vijay Subramanian, because I started my career, right? My PhD was in mathematical logic, master's, and my PhD was in complexity theory. So I really, and then I went into, you know, I sort of followed my husband wherever he went, and then sort of built my career. And so I kind of got into cybersecurity actually by chance, actually in 1985 at Honeywell. And so since then I've been working in cybersecurity and data science. But in any case, I think I really sort of like formal methods, but I haven't done it in a very long time. But computations over big data require massive amounts of resources, you know, third-party service to outsource some computations to be cost-effective. So when third-party survey is using computation, data becomes available in untrusted environments, either observed by man in the middle during transmission and so on, or inside a threat. So some of us, although I haven't been really very much involved, I've written a few papers and participated, but my two colleagues, Latifa Khan and Murad Kantajulu, have done a lot of work on secure encrypted data stream processing and using the Intel SGX platform and trying to, and I'll show you in the next chart, so using advancements in embedded hardware technology. So we built a very nice lab that's taking advantage of all these technologies to carry out trustworthy analytics. But there's also another part, right? Formal methods is where I really think that that's sort of going to be the solution for this, for machine learning, including logics for specification, deep learning, and verification of the machine learning algorithms. So what are the specifications for these machine learning algorithms? That's challenge 1. And challenge 2, what types of formal methods or theorem provers do we need to formally verify that that the specifications are met, or they are not, there is no covert channels or malware and so on. So you really need to, we really need more work in this area, and hopefully, the agencies will fund more research. And I believe that that's the way to go. Now, we know that formal methods is, it's expensive, but I think there's really no other way if you want to make sure, at least at this time. And, I'd like to have some discussions maybe later on, if we have time at the end of the presentation, what the audience thinks about this particular aspect. Okay, so this is again the Intel SGX platform. And essentially what we are proposing, right, what we have done here is that security critical functions, the data analytics, right, they are being executed in enclave memory, in a secure memory locations. So as a result, you can protect them. So that's really the whole idea here. Okay, so that sort of ends part 1. Now, part 2 is with Professor Alvaro Cardenas. He's really an expert in cyber-physical systems. And so he was my colleague for many years, but he's now at UC Santa Cruz. Security and privacy for Internet of Transportation and critical infrastructures. Okay, so Internet of Things, I think, I don't need to explain this, but of course your phone is connected to your refrigerator. It's actually scary, right? Because there is my camera, right? And I really need to, I really try to protect it, right? But sometimes I forget. Somebody could hack in and see, what's going on. So your cameras are connected to your televisions, to your refrigerator, to your microwave, and to your cars, and to your everything, your laptop and your desktop and your iPhone and so on. Similarly, for transportation, because now they've got internet of all kinds of stuff, financial things and medical things and transportation things, right? So all of your cars and vehicles are connected to the trucks and to the roadworks and so on. So this was published in Usenix Security last year, and then we have another paper that's coming out in Cyber Physical Systems security workshop at ACM CCS. So anyway, so IoT, major implications in the transportation industry, right? Autonomous vehicles, improve day-to-day activities such as delivering packages, improving traffic, and so on. In the US alone, right, 63.3% carry in the US, trucks alone carry estimated 63.3% of the freight of goods. AVs are not limited to ground, right? Also aerial and sea. Wide range of applications, levels of automation range from 0 to 5. With some interesting results though, with current ground vehicles in the market having partial automation, only 2, whereas aerial vehicles have an automation of 4, right? Companies are investing heavily. GM spent $728 million in 2018. And I also want to confirm, yes, they did increase to, I think, close to $1 billion in 2019. And we need to get the 2020 numbers. While there is great potential in AVs and their improvements it can do to the transportation industry, security and privacy concerns pose huge challenges, and this has to be addressed. I get really concerned about the security challenges, right? What if you have all these malicious attacks, and when you are driving, it's tough having to drive even without the attacks, right? So, I'm always struggling with driving. I don't know why, it's just very hard for me, but I do drive. But imagine if there's also attacks, it's going to be horrible. And so, right, so security of autonomous vehicles, AVs evaluate their environment using a variety of sensors, camera, GPS, inertial measurements units, and LiDAR, radar. So previous research has shown that sensors are susceptible to malicious tampering, like IMUs are susceptible to sound waves, GPS receptors are susceptible to spoofing, and vehicles should verify the veracity of sensor signals before acting, right? So sensor-based, right, AVs rely on sensors to evaluate and interact with the environment. And inherited issues. Sensors are susceptible to GPS spoofing and transduction attacks that manipulate environmental physical signals. And then the needed defenses, what do we need? Classical computing security, memory protection, cryptography, authentication, does not protect against these types of attacks, right? So maybe some protection, but these are much more complicated. And again, it's a real-time nature, right? Real-time constraints, AVs trust and act upon sensor data without any form of verification. So this is really going to be a challenge because of the real time, can we apply all these formal methods and so on, right? So that's a challenge. So our approach, what we did actually for that paper, it's very straightforward, at least now to build, but I'll tell you where the complexity is. So build a reference monitor, physics-based, right? Modeling all the physical properties, PBAD algorithm for ground. We did it for ground and aerial vehicles. So my contribution here was more on the machine learning part, which was really exploring. So, and also contributing to the algorithm. So it consists of 3 parts, not the model. Model was all Dr. Cardenas's work because he's a control theory, control system expert and cyber physical systems. So building a model offline of the AV's physical invariance, implementing an online tool to monitor expected and observed behavior to detect the anomalies. So, and raise an alarm if significant residual difference exists between executions, right? Offline pre-processing, online verification, and anomalies. So you could ask the question, what's the big deal here, right? So again, my part here was sort of fairly straightforward, but Alvaro was really, built a very complex model because you really need to understand what this physical system is all about, right? So this is the model that he developed, right? So K is state, Y is input sensitive measurements, commands to rotors, and then of course X, Y, and Z, axis moments of inertia needed for nonlinear equations describing drone behavior. M is the mass, and D is the drag factor, and B is thrust. Okay, so offline, the AV's invariants are calculated using well-known nonlinear models. Accelerometer, gyroscope, and magnetometer sensor data. These are the X, Y, and Z axis or Z axis is used for aerial vehicle. Vehicle position and steering angle is used for the ground vehicle. The online stage, it was, you could say we used extended Kalman filter, which has been around for a long time, right? So we made it simple, but in the future, that's where machine learning comes in. Is used to predict AV's physical behavior by estimating the unknown parameters, right, from the noisy sensor input. And the algorithm is divided into 2 sections. It predicts and corrects the estimation before it is compared against the sensor data. Anomaly detection, right? The CUSUM, it's a statistical model-based algorithm, is then used to detect persistent attacks, and alarm is raised if the residual difference is larger than a particular threshold. Okay, so the complexity was essentially the Kalman filter part and the analytics algorithm was, for me, actually, it was something that was very interesting. I learned quite a bit on this project. And then the model was, of course, that's really where, because if you can't model the physical properties, right, then really it's going to be, the results that you are getting is not going to be worth much. Okay. So the physical implementation, as I said, we use drones. So our students were walking around with all these drones and they were sort of interviewed by, people are really excited, right? Several news articles talked about Dr. Alvaro's work because whenever you see, because these are very real things. We are driving, we are flying airplanes, there are drones all over the place. So this is really the challenge. Aerial AV, Intel ready to fly zone. Controller, PX4 flight controller focused on detecting the attacks, GPS spoofing and gyroscope attacks. GPS spoofing detected after 0.2 seconds, gyroscope after 1.5. There was an overhead of around 5%. At the ground AV, it was custom built on top of Traxxas Ford Fiesta, Rally Chassis, controller ROS kinetic cam, focused on detecting visual attacks on the camera. Because remember earlier I talked about that aerial vehicles are susceptible to certain types of attacks and land vehicles to certain other types. But the attacks were detected fairly quickly, 0.1 second, and overhead was just 2.25%. Each threshold produces a probability of false alarms of approximately 2%. Okay, now we come to privacy. And not much has been done on privacy. So that's really where the challenge is. And I'll talk about the future next, part 3. But before that, beyond the security of individual vehicles, transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors, on lampposts and surveillance cameras to help identify traffic jams. Okay, so without a doubt, machine learning, data analytics and so on is really important to detect traffic jams and the best routes and various other things. But from a user's perspective, privacy concerns, because I may not want people to know where I am, or I might be smoking in my car and I don't want people to take photographs of me and send it to my insurance company, and then I get charged a very high premium. So, but again, there are some others say that once you get out of your home, forget about privacy. Even inside your home, I don't know how private things are, right? Like, as I said, the camera, somebody could attack this camera and, my presentation could be stolen before I give it on Monday. And so, right. And the driving patterns, I certainly don't want people to, take pictures of my driving and then send it to my insurance company, right? Although I've had for the last 10 years or so, I've had a very clean record. So earlier, actually, my problem was I drive too slow. And so I have been stopped by police 3 or 4 times for driving too slow. It was not even on the highway, on the left lane. And then when you drive too slow, then they also give you endangering traffic. And then on top of that, I also stopped on the left lane. So they said blocking traffic. So once I had 3 tickets. So now I always go on the right lane. So to be cautious, and only if I have to turn, I move to the other lane. But anyway, so legislators, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving the public perception. Okay, so I'm going to combine 1 and 2, right? So that's where I think the challenge, and that's what we are trying to do now. Okay, so this is really short, the part 3. That's our current work. How do we apply SecAI? Means integrating security and AI, or data science, machine learning. I'm putting the whole thing into one for Internet of Transportation and infrastructures. Right, so data science for transportation security, right? Internet of Transportation subject to attacks like any other cyber physical system. Streaming data is being collected. So how can we apply our ensemble of models? Lots of the sensor data, what can be more rich than sensor data with respect to streaming data? Because it's continuously coming from all directions, right? And again, as transportation systems go electric, you also need energy conservation. Threats to the security of such systems could cause massive damage, including accidents, loss of lives, stranded on lonely highways. So data science, machine learning techniques are being applied. So my question that we are asking ourselves and trying to answer by developing some algorithms and prototypes, can stream analytics learning be applied, that we are applying to, say, financial data, telecom data, and so on? Can they be applied to transportation data? Because remember, transportation data is not really like just simple network traffic, right? They're much more complex, the sensor data. The main question is to understand the nature of the complex transportation data and adapt our stream analytics techniques. So that's what we are doing. And it should be also able to handle massive amounts of heterogeneous data. And of course, the second thing I didn't mention, of course, the model, the physical model has to be accurate, right? So we've got to work with transportation systems or cyber physical systems. And so we are sort of collaborating with those in the mechanical engineering department. And so trying to sort of solve this challenging or address AI data science to detecting attacks in transportation systems. That's one. Second, I talked about adversarial machine learning. As I said, initially I was quite interested in applying this to transportation systems. So let's see, the Internet of Transportation will be, we know that AI machine learning is going to be all over the place because we need it, right? For giving us information about the weather, not only that, more about, where the accidents are and driving routes and various other things. Actually, recently I was teaching a class on social media, analyzing and securing social media. There's also a whole area now on vehicular social networks. How can vehicles form a social network, right? I don't know, and try to advise each other, right? So that's becoming a very sort of, I won't say hot area, but we can expect to see more research in that area. Anyway, as I said, adversary is going to learn models about us, used by our vehicles, as well as learn about the data to train the models. Adversary will attempt to thwart the vehicle's learning process. Therefore, learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and vehicle. So what sort of game? It's zero-sum, Bayesian, Stackelberg game. So his research is only beginning. But I'm not really doing much research myself in this area right now with respect to transport. I started doing this, but then as I said, I'm questioning for adversarial machine learning, how can we apply, in theory, there are so many attacks, right? So how can we handle everything, all the attacks? And so, I only talked about 2 attacks earlier, the targeted and free range attacks, but there could be many more attacks. So do you have solutions attack by attack? So that's where I'm sort of struggling with this. But then, okay, so but still with respect to research, I think we should continue, right? In the sense that who knows, because there could be something interesting that we can discover, or it could also lead to some new research problems, right? So with respect to privacy, this is where I'm very interested in terms of data collection, storage, analytics. Instead of a smartphone, now we have a little car here, right? So radar, GPS, cameras, LIDAR, it's all being collected, and some data could be encrypted and stored in the cloud because you can't, because sensor data, right, rapidly arriving, you need to do some very quick analysis, send the data to the cloud for further analysis. So privacy-aware, policy-based framework, data management for Internet of Transportation. So what I'm saying is data collection, data storage, data analytics, data sharing, all of them have to be based on policies, right? You can collect certain data, you cannot collect certain other data. You can store certain data, but not others. You can do sharing according to policies. And so privacy-aware autonomous vehicle. And on top of that, we need to first of all figure out what to do here. And then on top of that, you can also apply blockchain, distributed ledger technologies to ensure that all of the policies are enforced correctly and they are not, all of the work is done, and also security is maintained. Again, policies are, you can think of policies as contracts. Okay, my last chart, developments in integrating cybersecurity AI, right? It's exploding. That's really a very, very hot area. Applications of AI for security, that's something that has been, we've been doing this work. In fact, when I was at MITRE, we started this work in the 1990s. And there is a lot of very interesting work like Wenki Lee at Georgia Tech. I mean, he's been doing some brilliant work for a long time in this area. And so that's really the challenge. But now we are talking about models that are changing, concepts are changing. That's what we have, ensemble of models and real-time streams, massive amounts of data. Also, developments in privacy-aware healthcare and managing one's activities, privacy-aware quantified self. And we have some, brilliant people in this area, like Moti Jung and others have done some very good work on privacy and so on. At the same time, with the development of the Internet of Things, including Internet of Transportation systems and infrastructures, security and privacy solutions being developed, right? Physics-based solutions. And as driverless cars become a reality, more and more AVs will use AI ML, right? We need that. How can we develop AI solutions for detecting malware in AVs? And how can adversarial machine learning work, right? I'm not saying just because I'm thinking, whether is this the way to go, because I really want to learn more about this adversarial machine learning and applying game theory. I'm not saying we should stop this research, because we really should forge ahead, because we can find solutions to some problems. And research is always useful. If you can't apply in one area, you can, because I did some very, back in when I was doing my PhD on complexity theory. And then probably like 10 years later, I applied it when I was at MITRE, applied those results to inference problem in databases, analyzing the complexity of the inference, where you can put collections of data together, unclassified data, and infer something that is top secret. So research is always useful. And the next is privacy-aware policy-based data management framework for Internet of Transportation. So I talked about that. I believe that's the way to go, and combine it with blockchain. And this whole question of trustworthy machine learning, analytics efficiently when so much data, right? is coming from all directions. So I'm not saying that formal methods is a solution or SGX platform is a solution. Even if you are doing formal methods, remember, massive amounts of data, complex data. So it's not going to be straightforward. We can't maybe apply the traditional techniques of formal methods that we did, because formal methods was really hot, in the 1980s and 90s, but now it's coming back. And so what sort of specifications do we need? What are the verification methods? But nevertheless, for us researchers, there's numerous opportunities for substantial research and development. So that's what I want to leave you with, because there are so many research problems to tackle. I have again, my talk was very broad, covered a lot of topics, and some of these areas are well thought out, especially applications of AI for insider. There's also a lot of adversarial support vector machine, adversarial deep neural networks, adversarial this and that and the other, just like privacy preserving decision trees, privacy preserving association rule mining. But that's great. But what are we also need solutions that we can apply, right? And so that's also something that we have to focus on. So that's the message. Okay, now, again, the contacts, you can contact any one of us. Myself, for cyber physical systems, it's Professor Cardenas. For adversarial machine learning, game theory, Murad Kantajulu. Also with privacy, he's done lots of work on privacy, starting from his PhD thesis. Latifa Khan has done some very interesting work on stream analytics for insider threat and ensemble-based algorithms, and he's applied it to a number of applications, including for healthcare and medicine and so on. And Dr. Raul Quinones, he was our former PhD student. He's done some very interesting work and continuing to do this work. And of course, Miss Rhonda Walls, our project coordinator, she keeps us sane. You can also contact her if you want to contact any one of us. Okay, so that's the presentation. And I'm going to now stop sharing. And sorry about this. Okay, so, and again, thank you again for inviting me to give this presentation, a keynote presentation. I'm really honored. So I'm going to now email this presentation to the conference organizers shortly, but I will be there on Monday morning, my time, I think afternoon, I would say London time. So I need to check the schedule to make sure that I'm present. And so I will see you all on Monday, September 6th, and looking forward to having hopefully a discussion. I hope that we'll have time. Yes, I think maybe we'll have probably about 5. I went a little bit over, I think. So again, thank you very much. And I will see you on Monday, September 6th. Bye.